Okay.
Good.
Cool. So I've been working on this project involving stochastic synapses and trying different versions of it. And here I'm gonna talk about some of the results and also a surprising result that caused me to kind of reframe what's actually going on. Because I find that often with these neural network experiments, you get these empirical results and you have these stories of why they're working. And sometimes the story can be out of sync. So you're trying to figure out the right story because that's the thing you can carry forward into later experiments. And my story for this kind of changed a little bit over time. So this all started with this paper, the L0 regularization paper, which...
Marcus, can I ask you a very high-level question first? How relevant is this to neuroscience? Is this really a machine learning topic, or is this actually going to span both what you're talking about here? Do you think this is a biological explanation of synapses? Where are you on that spectrum?
It touches on neuroscience, but this is more of the machine learning type. The results and stuff I'll show today are more machine learning, for example.
You're not moving in a direction of like this explains something about biological synapses as much as this is something that's useful for machine learning.
It's more the machine learning thing right now.
Okay.
Yeah, it's more the machine learning. I could talk a little bit about how it...
I just thought it's important because we have people who've been following our work for a long time. We've talked a lot about synapses, but biological synapses, and so this is really not that as much.
I mean, like synaptic failure does exist. To that extent.
I'm just saying, but you can end up completely different.
Yeah, no, it's more machine learning.
Results based on what you're trying to accomplish.
Right.
So,
could we alternatively could we think of this as a mathematical way to think about stochastic synapses and permanences in biology?
Yeah.
So some mathematical insight into that.
Yeah, I would say like it's kind of a stone's throw away from biology, but here I'm more focused on results.
yeah.
And
Okay.
so.
Let's just
We can circle back
but
afterwards.
later we can come back and maybe see if it's relevant. A lot of things in machine learning and neural networks don't really have a lot of relevance in biology, but they're a stone's throw away. So, okay, got it.
Yeah. So something I presented some time ago was this paper that made the synapses in the network. Here I show this unit I projecting to unit j with a certain weight. But this weight is actually the stochastic weight where it gets multiplied by this gate, this z value that is somewhere between 0 and 1. And so this is their way of having synapses randomly fail as a way of kind of seeing, is it okay if the synapse fails? Can I prune it, basically? And I thought it was a really nice paper. They used though this distribution, so this z, this gate that's between 0 and 1. They came up with their own probability distribution. They called it the hard concrete distribution, where this random variable, the z, is sometimes exactly 0, sometimes exactly 1, and sometimes it's somewhere in between. They get good empirical results. My only complaint with it is that this feels very invented. It feels very just kind of cobbled together. It feels like they put something together and it worked, which is cool, but I would like something that feels a little more fundamental. It'd be nice if you could get it working with straight up Bernoulli random variables. If you have this gate that's either 0 or 1, it either drops it or it doesn't. And so I put time into figuring out how to do that. I've presented this to a few of you, so just very briefly. Here, okay, the gates are this Bernoulli random variable where you're training the probability. You're training the probability of this gate being 1 or versus being 0. And I've adopted the language of calling this parameter a permanence. And permanence is something that we've used in our models here, and I've kind of co-opted the term because it's conceptually quite similar. But I've added this notion of it being the parameter of a stochastic variable. So after thinking about this for a while, how to do it, I realized you could.
Just make clear about
Yeah.
it. It's really not the same thing, though, right? I mean, there's nothing in our previous usage of the word permanence. There's nothing stochastic about it at all.
Right.
It's
That's
more of
the
a training
difference.
parameter that lets you know about something about the history of the synapse. So I just want to be clear in my mind that I really should try to equate those two at this point in time. They're in the same field of study, but they're really different things. That would be correct.
I guess it's just one is with our permanences, if it's above a threshold, if it's above usually 0.5 is connected. If it's below, it's not connected.
But the whole
And-
idea of it is that it represents an accurate historical trace of
Yeah.
some sort. It is not there as any sort of stochastic process. It is a gating factor that moves you from 0 to 1, but it represents something very different.
So so this is still that, but I've taken it and I've made it where when it's near the threshold, it's stochastic.
Okay, so it still represents a history.
Yeah.
Okay, the same type of history or a different type of history? We'll get to that.
It's very similar. Right?
It's very similar. The only thing is usually when we do it, it's something along the lines of Hebbian learning, whereas here it's more keeping track of an error. It's keeping track of whether this synapse caused harm or if it helped.
All right, so you're adding a little bit of stochasticity, I don't know what it is, between the 0 and 1. Is that?
Yeah.
Okay.
Yeah.
And that's important, I guess, in this case.
Yes, it is. But my reasoning for why it's important changed over time.
And it's just in my mind, the history of synapses, there's always been this sort of randomness to them, and it's been studied in various ways. And this, they've been talked about being stochastic in biology. But that's never had anything to do with the way we thought of permanence.
Mm-hmm.
There were separate fields to study completely. And that's why it's confusing to me to say, oh, it's a stochastic process. No, but I got it where you're coming from. I just wanted to clarify that.
And I have done experiments where I got rid of weights. I'm not going to present this here, but where I got rid of weights and I only trained the permanences to make it more biological. And this update rule works for all of that. So I haven't prepared that for today, though. Anyone wants me to go through this? This is the derivation showing that this is an unbiased estimator for the gradient, figuring out how to change this parameter so that results improve. The trick being that you are, just very briefly, you're doing the gradient with respect to the expected error rather than with respect to the error itself.
Right.
And then through running through a couple steps, Monte Carlo approximation where you're just looking at an individual wave, and this Taylor approximation, it ends up becoming this super simple thing that is also known as the straight-through estimator. Bengio has written about it. Other people who have written about it talk about it as being something that just empirically works despite being biased, but despite being a biased estimator. But in this case, I make the case that it's not biased. For a Bernoulli random variable where you're changing the parameter, it is actually an unbiased estimator. I can talk about that with anyone who wants me to go into it deeper, but I figured I'd just put that out there. Okay, so this I understood. This is theoretically appealing. This is like you're treating all synapses as these probabilistic gates, and you're just tweaking. You're figuring out, should this one fire, or should this synapse exist? Should this one? And it all makes sense.
It's still a multiplier on a weight, is that right?
Yeah.
So it's not really the synapse is a 1 or 0.
But
it's really whatever the weight is, it's either there or it's not. Is that
Correct.
Okay.
Correct. But I also can run experiments where I hold all the synapse weights fixed, either all at one or all at random numbers, and just train these, and the results are quite good.
Okay.
I can do all of that. However, today, since I'm really more focused on the ones where the weights are trained and where we're training sparse networks and et cetera. So this was like, this felt good, it worked, the results were nice. But then I through some experiments, I also tried a deterministic one that is a lot more like our classic permanences, and that it removes the stochastic part. I use the same thing I derived for Bernoulli variables, but instead I just if the theta is above a threshold, it's connected. If it's not above that threshold, it's 0. But use this rule. And I was surprised to find that this, in many cases, works better than this. In some cases, in the general case, this is better. But the fact that it worked at all made me. The fact that this worked at all made me kind of uncomfortable because I no longer had a theoretical understanding of what's going on here, because I derived this. This is just cobbled together. It's strange. So as I wrote here, the surprising result is the deterministic approach works pretty well despite being cobbled together. So I found myself in a place where I needed a different story of what's going on here. And it actually gets a little bit into how you were just describing permanences, that they're like a record, a history of whether this synapse has been good. So I call this tracking a synapse's usefulness with permanence. So a different narrative I'm going to put on all three of these methods is that what I would have said before is that the network has all these stochastic synapses and it's trying out different values for them and seeing which works and moving in that direction. And through the power of randomness, it arrives as something better. That sounds good, but the fact that this one works made me realize that that's probably not the right story. And so the new story I'm putting on this is that all these methods are doing something like having this parameter that's somewhere on the number line. It's called a permanence. And that parameter is being pushed in one direction by a constant decay. I didn't mention that, but in these methods, typically what you'll do is have the parameter decay over time and rely on the error gradient to push it back up. So in general, what you have is you have this.
The threshold is decaying over time.
No, not the threshold. I'm sorry. Sometimes we use theta as a threshold in our papers. Here I use theta as a general parameter. I could have called it p, but I use p elsewhere. But it is the Bernoulli variable. It's the thing that's underlying this. Is the permanence. What's going on here at the core?
So if it's decaying over time, that means the pressure is to be sparse.
Yeah.
Okay. Right.
Yeah. But what's going on at the core for all of these is you have this parameter called a permanence. It's being pushed in one direction constantly, because we're kind of incentivizing it to be sparse, and it's being pushed in the other direction by just the standard gradient techniques of trying to improve the error. And basically, if it falls below this threshold, it gets pruned essentially. If it's above the threshold, it's kept. So the core algorithm is, you could say that what this is really doing is it's implementing some notion of, if the average of the error gradient is above some threshold, then keep the synapse. Now, this notion of the average error gradient is very flexible how you do it. Do you take the average of this over time? Do you weight the recent ones more highly than the older ones? There are different ways to do this, but at the core, the algorithm's kind of doing this. And an interesting thing is the permanence is not itself the average error gradient. It's more just that this algorithm is being implemented, but no. Something that's kind of strange here is that if the gradient is above this, it's just going to keep increasing endlessly, But in the top, it's stuck at maxed at 1. I can choose to do that, but that's just kind of it.
Isn't that? I'm sorry, I'm missing. Isn't this the?
No, that's the connection is either 0 or 1. So that's switching between two states.
Oh, this is
but
this is the
parameter
gradient.
that conditions that is unlimited.
Okay, all right.
I can fix it at 1, but
Okay,
like
I'm just trying to confuse,
yeah.
clear up my confusion.
So this could be anywhere on the number line. This could be 42 and this could be 44, and the threshold could be anywhere. There's nothing essential about the numbers 0, 1, and 1.5 for this. But at the core, this is I think this is the right story for what's going on here. But there's also the fact that like the randomness, the stochastic part, does help in many cases, and I found that today in the results I'll show that the randomness is still needed. So I think that these are kind of separable.
Well, but didn't a moment ago you just said it wasn't needed, right? I'm confused. I'm not trying to challenge you. I'm just confused.
It works surprisingly well without the randomness.
And you said something you might think are even more better. You said
I found when I trained fully binary networks where even the activations are binary, that suddenly this was better than this. So it depends on the experiment.
Okay.
But the thing that remains true across all of those is I'm surprised that this worked at all, or I'm surprised that this did better than.
But do you have a understanding of why with binary that works better? The deterministic works better.
The explanation I would give is that is you want your network to have some form of regularization. You want something that keeps it from memorizing the data set, essentially. And
but that's
one
true
way.
For both of these. Both of these are kind of irregularizing.
I don't have an explanation for that. You're right. I think it's just that. I think here's the answer: is that when you have binary activations, that's almost itself a regularizer. And once you add even more stochasticness into it, at that point you're just making your training really random. So you want some amount of regularization. You want some amount of randomness, something to. But if you have too much, then it gets worse.
I have trouble with, and I'm just my ignorance. I'm sorry, but I have trouble understanding how the randomness helps at all. If I'm just trying to look at historical track of how valuable the synapse has been, and based on some previous amount of data, that seems sufficient to create new synapses and get rid of synapses. So I don't have an intuition why the randomness helps.
Yeah. So
you're saying you have intuition why the randomness helps, but you don't have intuition why the not having it work.
Sure. So I'll say that the final bullet point here is like if the randomness helps because and this is like a well documented thing that that networks, if they don't have something stopping them from it, they're going to overfit. They're gonna do something that's analogous to memorizing the training set.
Meaning like a local minimum type of thing. Is that another way of putting it that way?
In the
it's not really a
energy
global
function
minimum.
sense.
It's just it could be a global minimum in the training set, but it's very different from what you need in the test set. Basically, it's you overfit to that. You find patterns in the training set that are just there in the training set.
Yeah. Modeling noise, essentially.
Modeling noise.
Yeah.
Yeah. So like just to put this very concrete, like one of the classic deep networks is an 8-layer network, AlexNet. It uses dropout. It drops out in its top few layers. It drops out all of its units with 50% probability during training. If you remove that, if you just train the network, it achieves 100% accuracy on the training set and 0% accuracy on the test set. Without the dropout, it literally just, at least in my experiments, it memorizes.
So I think this field has been around for a long time. I remember reading papers about how neural networks perform better with the stochastic elements and going back, I don't know, the 80s or 90s or something like that. I'm not sure if that's the same basic genre result. But I always felt it was weird. It's like from a brain point of view. I felt like, and so now our understanding of what's going on in the brain is a little bit more sophisticated than this. I mean, the brain just doesn't get a bunch of training data and train on it. As you and I have discussed a lot in the past, and this team has discussed, there are multiple types of representations that are going on, and the concept of generalization just comes about because, we can call this generalization, right? I have a training set and I want to generalize it to a broader data set. Well, I don't think the brain does it by introducing randomness. I think the brain does it by having a more systematic way of discovering, this, if we want to go back to displacements, of discovering the underlying generalized structure which can be applied in different situations. So I'm only saying this just to make sure I place this in my mind of what's going on. In the classic neural networks, I can now understand where you're coming from, that this helps. I can see why. But from a brain point of view, I don't think that's what's going on. This is overcoming one of the limitations of simple artificial neural networks as opposed to fundamentally discovering how brains generalize from training data to non-training data. And I'm just saying that to see if you would disagree with that or not.
I think that's fair.
Okay, then keep going.
Okay. So this is pretty much the end of the whiteboard part of this. I just wanted to correct my story, basically. That and I have this hypothesis that these are kind of separable things. You don't need the synapses to be stochastic. However, the randomness does help during training. So I kind of went into this with this idea that maybe things can work if you use the deterministic approach while having some form of dropout in the network.
Question about, I think that's a really nice way to phrase it, what's in the rectangle.
Yeah.
It's very analogous to stuff we do in the temporal memory, I think, in some ways. But one difference, if I understand it correctly, is if you have sparse activations, I don't know how that will impact that, because most of the time 90% of the time the gradient is going to be 0 or whatever. And so I don't know if you need to think about that, especially in our temporal memory. If the most of the time there's no change to the synapses.
Right. Then it jumps, so the variance is very high in your feedback signal. But then it jumps when there is a signal to be captured.
Yeah, when there's an actual error or a success, then it happens. But most of the time, if it's silent,
Are you talking about
you're
just saying the dendritic segment?
Yeah.
On the dendritic segment, none of this happens if that dendritic segment's not involved.
Yeah, if it's not involved and the cell doesn't fire,
Yeah.
we don't really do anything. And it's actually that, I think that's critical in our temporal memory.
Yeah.
I'm just wondering, when you have sparse activations, you need to kind of reformulate this or think
I-
about it, or maybe it's just a lambda. You just have lambdas.
Is it really
No, I
sparse
totally
activation,
agree.
or is it, I guess it's sparse activation, yeah. Basically, whether the cell's even participating or not.
Yeah.
Yeah, I totally agree, and I guess part of why I wanted to write this out was it exposes its naivete that like there are that it's going to have flaws in certain situations, and maybe it's in some ways it's strange. Like I just pointed out the case that can just increase indefinitely if you don't do anything about that. It raises questions of, is this how we want to do permanences? If this is the core algorithm, if you wanted to go at this straight on, is this what you would design? I've run a couple experiments trying other things, but I have nothing to report there.
And I guess I would ask, since we know we want sparse activations, how would we reformulate, or do we need to reformulate?
There is this interesting work of Stefano Fusi, right, on metastability or metaplasticity of synapses. Actually, 2 papers. One where the synapses are stochastic and have sort of like a probability of dropping out that is proportional to their learning significance, although that is a Hebbian associative learning rule, because he's talking about memories. And one where he has a multi-stage level of metaplasticity in the sense that the plasticity changes over time, so which turns out to do the same thing. It's again discovering that many of these things are like homologous in some sense. What I wonder about a lot, because it's such a big thing in biological models, and it is a concern for machine learning models too, is the homeostasis of all of this, right? As you pointed out, that error that could push on pushing your permanence forever. And so the question is, how do you bring it back down when it runs away? Biologically speaking, there's always limits to it, like any biological processes, it is limited, and the brain is full of homeostatic mechanisms. that make sure that a neuron that is, like overexcited, like changes its threshold, and a neuron that hasn't been participating forever, is like increasing its firing. And so in that sense, I wonder, because there's two different ways to go about that. One is to scale the error at the individual synapse, sort of in proportion to its its total contribution to the total error, for example, that gets propagated. Then you would know whether to change it more or less. Or alternatively, you could change the decay such that when you have too many synapses in the network, the decay is faster, so as to balance out any sort of overaccumulation of synapses to keep it sparse. Mm-hmm. I wonder how you think about that in the context of these models.
I agree that there's a lot of options. I guess that I'm basically setting up the problem, and I don't have a specific path forward that I'm going to vouch for right now.
Right. I just wonder whether any of these approaches ever show runaway problems.
Not that I've seen, but I also haven't. But it's also easy for me to let myself remain ignorant. I don't have to look at these permanences. Maybe some of them are a million, and I just haven't noticed.
Right. It's like a bit overrun, and it flips back into minus a million. I don't know.
I have a really basic question. This came from my education. Just take it back. We're talking about this during training and improves during training. Are all these scenarios, these options you talked about, were all those basically introducing stochasticity during training and not during inference?
Correct.
Okay, so this is all about a training paradigm. And once you train the network, then there's no stochasticity
right.
In the final network.
Right.
Okay.
Because inference is always just one pass up through the network. There's no notion of it just sitting and computing for multiple steps. Yeah. So it'd be strange.
I sort of recall there were some networks in the past where they showed that networks improved in their inference capability by adding stochasticity. Mm-hmm. But it could have been Cahonin nets or something. I mean, it could have been a long time ago, so I don't know. It doesn't make sense. You're right. It doesn't really make sense. What's the point of it at that point? Mm-hmm. But okay, thank you.
Right, I think I'll jump and show my 3 slides, and then if any discussion comes up after that, you can do it. So yeah, Matt, I'm starting with that first slide. I guess I don't know if I should put this camera somewhere else or what you want to do.
Make it refocus.
So I'm starting just giving context. This architecture here is what we use for most of our Google speech commands experiments. I'm just putting out in front and just talking through it briefly. So Google speech commands is it's a bunch of recordings of people saying the digits 1, 2, 3, 4, 5, 6, etc. And the input to the network is a spectrogram. So it's like this 32 by 32 spectrogram, which allows you to treat this as a convolutional neural network problem. And I've drawn a box around the 3 hidden layers. It's a convolutional.
Can I ask another basic question?
Yeah.
Does that mean that the 2 dimensions of 32, 32 are the same? That's why you can use a convolution network on it? I mean.
Well, they don't. The fact that it's spatial in any way, that we've taken sound and converted into something that's.
But if I had all low frequency sounds in one corner, all high frequency sounds in another corner, it seems it wouldn't be true that I could use a convolutional layer on top of that, which sort of assumes that the statistics are the same everywhere. Is that my misunderstanding?
It's amplitude in one direction, frequency in the other direction, effectively.
But so
I don't think that answers this question.
I have a more basic question. Maybe I just don't understand convolutional layers very well. If you think about vision, you say, oh, I have this picture. There's one assumption you can make, and it's an assumption that the statistics of any part of that visual image are going to be the same, and therefore you can copy and replicate, and that's basically what convolution does. But in a spectrogram, that's not clear to me that property is true, that different parts of that spectrogram image are statistically similar as other sections, and so maybe I'm misunderstanding.
So a couple
thoughts. You can still use it, but what would happen is, some of those 64 filters might end up representing low frequency components. They would only be active on the left, and the others that end up representing high frequency components would only be active.
Oh, that's right. There's a series of convolutional layers here. I see, yes. Okay, that answers I forgot that, thank
And
you.
the other thing is that the convolution doesn't necessarily have to be isotropic. It could be just, in one direction rather than, equally weighted across here. So you can learn the weights so that you could say, I'm looking at a particular amplitude and a range, a particular frequency and a range of amplitudes, or vice versa, because you could shape that convolution. It doesn't have to be like a 3x3.
Yeah, but there is an underlying assumption that there's some sort of statistical regularity that you're taking advantage of in an array.
Well, we'll find it if it is there, right?
Okay, fine, all right. I got it now because what I was missing, I forgot there's 64 of these convolutional layers. Sorry. Each one is appropriately doable. Okay, sorry.
Yeah.
Keep going.
So yeah, there are three. It's a 4-layer network: convolutional, fully connected. But the top one is sort of different in the fact that it's a linear classifier where the number of units is the number of cells. It kind of gets treated a little differently. So I've just drawn a box around it because sometimes we focus in on the hidden layers and treat the top one a little differently. For example, we would never want to run k-winners on the top one, but we'd use k-winners on the others. Those kinds of things. So this is just context. Now, slide full of data. Here, the columns on the left, I've labeled this using, those are pictures of the layers.
But I have new numbers for these, so.
You have what?
I have new numbers for the left side, so I should give those to you for the slide.
Oh, new numbers, got it. I see what you're saying. Okay, yeah, so these are numbers, the left side of this is numbers from the How Can We Be So Dense paper. I've color-coded a lot of them yellow to point out that it's sort of unfair for me to try to compete against the yellow ones because that wasn't really trying. The How So Dense paper was mostly focused on the other layers. It didn't try for sparse connectivity in the convolution.
But now I do have it.
Okay.
What is 100%, 40%? What is that 100%?
Non-zero weight percentage.
So yeah, this is almost all the numbers in this, except for like the bottom two rows, are non-zero weights, which is to say synapses that exist.
Okay, so when we say how so dense, sparse, that's not sparse at all. You're saying 100%.
So
it's actually a density figure.
Yes, fair, but that's not what Jeff's saying. The only relevant rows to look at for the left two columns are the non-yellow ones.
Oh, I see. Yes, I get that now. Okay, I got it.
The others are correct, but also outdated, as Subutai just pointed out. But also they're kind of polluted by the fact that those older results didn't try.
And when we say thousands of units, that's synapses per unit?
Yes.
Okay.
Yes. And so the main thing to compare to on the left side is the two grayish blue numbers, and of course the bottom, the classification accuracy. So on the right side of this, before I go into the numbers, I did two approaches. One, I did stochastic synapses, and second, I did deterministic synapses with permanences. Both of these have permanences, but I found I needed to introduce traditional dropout of units to bring the results up, to make up for all of that. So I had to do both. And I guess we'll start by looking at the fully connected layer, the one that is blue all across or gray all across, and show that like the How So Dense paper fixed the sparsities at 40% and 10%, and showed that it could achieve good classification accuracy with those. With this, I've gotten down to when I aimed for similar accuracy. I got down to 5% in that layer using this approach, but I also used this approach in all the other layers, and it was able to bring the sparsity of those to be quite good. And
just a question.
Yeah.
How did you try that? It's a high-dimensional space to be operating in. What was your way of finding out what sparsity you can go for in the different layers?
I used the same lambda for all layers. so I didn't try to do a very good job.
So the best numbers might actually even be different.
Oh yeah, the better is definitely possible.
Was the super sparse house so dense? If you went below 10%, did it not work well? Or why did you stop at 10%?
I'm just using the results that are there, so that's more of a Subutaian.
Why? I mean, you're saying, hey, you got the 5%. Could you gotten to 5% with house so dense? I mean, without this stochastic stuff, did it not work at that level? I forget.
Back then, that was the lowest I could go.
Before what happened?
Before the accuracy.
Accuracy dropped off. I mean, because here the accuracy is only marginally affected. So you're saying if you went below that, it started to get significant.
In the more recent results, I have better accuracies now, and I think I think it goes down to 5%. Yeah, that one.
Do you know what changed?
Sparsity in the weights.
I hope he knows what changed.
But yeah, so I've also included sparsity in the CNN layer. So all of these numbers will change.
Mm-hmm.
I can tell you the CNN sparsity is nowhere near as good as what Marcus is showing. So this is much better. And the basic reason why the house of dense technique is not going to work as well as this is that we just set a static. We just say these are the weights that are going to be sparse, and that's fixed all the way through. Whereas here, he's actually dynamically figuring that out.
But also here in the yellow columns, I guess they're saying these other layers are 100%.
Yeah, now they're closer to like the first one where he has 34 and 24.
Yeah.
I think mine are like 50%, somewhere around there, 60%. And then where he has 16 and 9, mine are like 20, 25%. Like that. So it's much better than what I had before, but it's not as good as what Marcus is showing. And I don't expect it to be as good.
And then
the top one is interesting because I haven't even thought about it.
Why is it, Marcus? Why are you suggesting we only look at the gray area there? Why is it not appropriate to compare the yellow 100% to your 16.9%? I mean, why wouldn't I be comparing the sparsity across all its layers?
I feel because we hadn't really pushed those to their limit yet.
I see. So
on
it's
this
not
other
fair
approach.
to do it. We ultimately we care, but you're saying
we care.
Subutaian hadn't done that yet, or we hadn't done that yet. Is that the idea that we haven't really pushed on that?
Yeah, that's it.
Yeah. Like the 4% number is really good, for example, in the right column.
The bottom one, all layers.
The gray.
Okay.
The full.
Yeah, 4% all the way.
You're not saying.
I'm at 5%. Yeah.
Yeah. So I mean, 4% is better than 5%, but not super better.
No, but all of these numbers, you don't have the total non-zero parameters here, do you?
That's what the all layers is.
That's all layers is, right?
Oh, okay. The 68,000 total. That's the total number of non-zero.
Yeah.
Okay.
So that's dominated by the second row up there, right?
Yeah.
Correct. Yeah.
So I do want to point out though that yes, it's dominated by the second row, but this is why I included the multiplies row in this. So it's interesting if you look at
I don't know what that means.
the number is essentially floating point operations. Floating point operations.
Physical multiplication.
Yeah.
Computational cost.
Yeah, it's but it's only the multiplications.
How did you compute that?
Simply by I didn't account for whether the units are zero, whether the activation is zero, and so this is something you can do with for a fully connected layer. The number of multiplies is the number of weights.
It's not the number of non-zero multiplies.
Correct.
Okay.
So you multiply zeros and all that.
Okay.
So you're correct.
Yeah.
So yes, this is a disclaimer here that if I had included the fact that that we're using k winners on the left side, the multiplies would improve because so many of the multiplications are with zeros.
Did you use k winners here? Or?
No, that's the thing. I tried. Monday night I couldn't get a good result with it. So
it's something related to that. Yeah.
Possibly, yeah, very possibly.
Do you use k winners on the left side? Though?
Left side, the right side. I'm just
the top. Because Lucas was asking about.
Correct. The top is just a classifier. Yes, the left side is the house of dense result.
This table would become really useful if one had a more uniform way of measuring these things, right? And a fair way of accounting.
Yeah, no, I think what Mark said is fine. It's just I wasn't sure what he was.
Yeah,
So,
so-
if you just look at the sparsity in the weights, this is the number of multiplies you would get to.
Yes, just by looking at the
Would
weights.
it be fair to say we need to get this to be more of an apples to apples comparison, but in the end, are those two bottom rows really what matter to us, the accuracy and the multiplies? Is that sort of the bottom line result that all those other numbers boil down to?
No, I think the total number of parameters matters, because that affects the memory size. That's
Memory
used.
size.
The other thing is not shown here is the noise accuracy. To me, that's the robustness
okay.
is important too.
So yeah, I'd say that the ways that this is not an apples to apples comparison in the sense that all those things are yellow. If it could change the color of those cells to a different color, then it would be pretty close to apples to apples.
Yeah.
Now multiplies, if you have a way of taking advantage of multiplying with zeros being optimized away, then yes, suddenly that's a really nice property to have. But in terms of
So again, let me just back off and say, okay, so maybe the bottom 3 rows, if everything got rid of all the yellow, the bottom 3 rows plus maybe a noise issue. But so the third row from the bottom is essentially memory. The second row from the bottom is essentially CPU computation time, and then the bottom row is accuracy. And I'm just trying to, that would be sort of the sum total of all the other data.
Yeah.
Those 3 really matter.
Yep.
Now you've introduced, you said we have to have another metric besides accuracy, right? This is
The robustness.
robustness, which is a accuracy with noise, is that what that is?
Yeah.
So then maybe there'd be another row where, under some sort of noise robustness test, we would have another accuracy.
So in the House of Dense paper, the robustness was done by adding noise to the input and seeing what the effect is of the classification accuracy. One of the other papers I read, they did a different thing. They trained the network up as you normally would, and then lock the sparsity of the network, and then tried training it against random noise. And to the extent that it could not learn the random noise patterns, they saw the network as being robust in the sense that it's learned what it needed to know and it can reject noise out of hand. So there's kind of 2 dimensions of that.
That's weird.
That's
What's the logic behind that?
The logic behind it is that you sparsify it down so it learns what's essential about the task that you've given it.
Yeah.
But you don't want it, you want it to be resistant to overfitting if you say turn on a continuous learning thing after that point.
But you're saying that you're training it on noise.
You try to train on noise.
But why would that ever really occur, or why would I be training it on noise?
It's an example of saying that if you you're for some tasks you're going to be faced with things that are not in that space, okay, and you want to be able to reject it. You don't want to, as in some of these.
That seems like a very specific concept of.
Well, it is, but it's a problem in machine learning because you can give these seemingly random patterns that go and come up with high results in some category.
Antagonistic.
Right.
Problems.
Right.
Mm-hmm.
So in the sense that we're not fooled by that random noise.
But this is a training issue, right? You're saying it's resistant to learning these new.
It's resistant to learning from that point on. So there's 2 aspects of it. I'm not saying it should be used instead of what we're talking about, but it's another metric. To say.
All right, I got it. But again, that's kind of a very specific type of problem they're trying to deal with there.
Well,
I mean, there's a lot of ways you could measure robustness. I mean, because there's limits, right?
presumably, but this is, I'm just saying that, it's 2 twists on the same idea.
Yeah, all right. I mean, as I said, you'll have to come up with some ways if we want to measure robustness. And there's multiple ways we go about it. So, but I consider it an open-ended problem, and so you'll just have to pick some things.
Right. Well, it's just that the problem with the existing networks is that they find solutions in some space, and they sometimes will react to noise in a way that says, I've got high confidence that this is a cat, and it just looks like noise.
Yeah.
And part of the argument is that when you have dense networks, that becomes possible.
Yeah.
And the sparsity is actually
Permanence.
prophylactic against that.
That's an absolute dense paper, right? It's like separating these spaces very clearly.
Right, but it's in our case, it was adding noise and seeing what how the values would degrade. This is one where it would say even reject against.
I got it.
Okay.
To one point I started to make a while ago, but was, as you pointed out, the number of parameters is dominated by that fully connected layer. Most of the weights are there, but it's important to note that if you look at the yellow rows, bottom leftmost, when the sparsity dropped from 44% to 15%, we're going from sparse to super sparse, the number of multiplies was barely affected. The number of multiplies is heavily impacted by what's going on in the convolutional layers,
That's right.
despite the fact that they don't have very many weights,
Yeah.
because those weights are multiplied many, many times. So
I see.
so it's important.
Big effect on that.
Yeah. So number of parameters matters, yes,
So
memory.
those weights are not the total number of weights in the layer, but the number of weights that you have to train on? Is that-
Yes.
yeah.
Yes. So the actual thing, yes, the number of weights, the number of multiplies is much larger.
That'd be like saying in the cortex, oh, go to V1, when are we going to count the synapses
Yes.
on the little section of V1, then we're done.
Yeah.
Okay.
Yeah. So
It's
it
funny,
is.
how do they get so low? It's like, well, how can it be so low? Anyway, 381, it's like, wow, how could that be?
Yeah.
Now we get it.
So this is pretty much it for this slide. But everything in this slide is legit, but there's something that is worth looking at. So yes, I have reduced the number of floating point operations, etc. That's all real. But the thing that is important to look at is how are the weights distributed through the units? Have I essentially killed a lot of units? Have I totally stripped a lot of units of all of their synapses? Or have I actually, gotten the sparsity of each unit down to something?
That's a good question.
That is.
So you want to look at what the network structure is in essence.
Yes, network in terms of the individual units. Yeah. So another information dense slide. On the left, I've just redepicted all of these layers, and I'm showing histograms of how many synapses are on each unit per layer. So the top would be like the classifier, which is you can mostly ignore. The bottom three are the interesting ones. And of course I've drawn the stochastic and the deterministic in the two columns. And
185 of 1,000 units of 0 synapses.
yeah, so this, because I've just gone with this naive approach of just performing this decay on everything, I didn't do anything to make it shoot for a certain target. If I wanted, I could come up with a way to say, I want every unit to have 10 synapses. Or I could shoot for some goal. I could do some sort of approach.
In essence, you're pruning neurons. You're not just.
Yes, that wasn't the goal, but yes, I'm pruning synapses, and in some cases, it actually ends up with some of them being totally pruned, especially in that fully connected layer.
Yeah.
And as you can see, the 185 of 1,000. This picture makes it look like there are 400 and some pruned, but some of them have like 2 or 3, just because I've zoomed out in a way to show the sparsity in context. But the point is, everything in the previous slide is true, but there's still things to look at, because I don't know unless maybe we wanted us to prune it to small networks, or maybe we specifically want to shoot for networks that all of their units individually have 20 synapses per unit, or I didn't do anything to shoot for a certain structure, and this is what popped out.
That would reduce the compute even further?
No.
No.
I mean, in
In some ways, this reduces the compute a lot more because
Yeah.
Right.
It might do better with the same number of units or something like that.
in the spatial pooler, we said, we have some fixed amount of resources, and we want to use those resources to divide
Yes.
up the input space as best we can.
Yes.
And so the best, that's what the whole boosting thing did, right? It made it divide up as best as it could. Okay, we got more resources, let's divide up these things. And so here we're not doing that here. And this is what you end up with. It's an interesting question as to I mean, I always assumed that we want to use all the resources. I mean, the brain uses all its resources. If you don't find parts of your cortex just sitting there dead. Maybe this is the old.
No, I'm guessing
that
this
was
is
my homeostatic argument, right? That if in neuron or a synapse that does not get used at all, will change to be recruited somehow,
No, but I'm not talking about synapses. We're talking about units here. This is right. I wouldn't have a problem with synapses. It's the fact that these units are not doing anything.
Yeah, right. So neurons that are not activated at all lower the finding thresholds.
I guess it's the difference between synapses and I see it's qualitative difference. Yeah. So this is basically saying, for whatever reason, the way we train these systems, half of the neurons just don't do anything.
And I would say it's not that it's not like the training algorithm here was some oracle that knew everything and it found the optimum. It's really this was a naive training rule.
Yeah, but it somehow feels more intuitively correct that we'd say, well, we got more resources, we can somehow do a better job by using it all.
Yeah.
That was the spatial pooler. So I don't know what the mean can make of it. I'm just saying, wow, that's weird.
Yeah. So there are clearly ways to try to solve this and make better use of it. I'm just putting out the fact that there's a thing to be solved.
If we threw in something like our boosting onto this, the spatial pooler type of boosting, would the results get better, or would they say, nope, this is the best I can do? For this data set. We had this issue too with the spatial pooler that under some limited data sets, there wasn't a logical way to use all the columns, all the spatial pooler bits, and in fact we had this thrashing about the boosting, which is sort of try to constantly there wasn't enough variety in the data to take advantage of all the neurons.
Right. So maybe you don't actually need all of these things.
It's interesting in this case. I mean, that's possible, I suppose, here, given that we're talking about these fairly small convolution layers, right? I don't know. I'm just trying to relate it to things we did in the past. But who knows? Okay, that's interesting.
So this is pretty much all my material. I just was laying out that the question of stochastic versus deterministic. I don't have a single thing to say as far as that's right or that's right. There are different things that work. It seems to be some mix of permanences or some mix of keeping a history of how useful a synapse is, and some amount of stochasticness mixed together causes good things to happen. But that's as precisely as I'm able to say it right now. And otherwise, that's it. Unless we have any talking, I can bring up the table or anything if we want to use it as a reference.
So what do you think we should do going forward? Should we incorporate this stochasticity in all of our work or not? Should we investigate it further before we go there? What's our thinking about?
I think we have to have some sort of dynamic sparsity. So using a static mass like I was using in the house events is not a good.
Yeah, I can agree with that. Okay.
So I think this could be a really good
one. But dropout's an alternate, right?
No, that doesn't do that. Dropout is a weird thing.
Right. Here both of the dropout was this extra thing I bolted onto this, but here both my stochastic and deterministic ones are doing permanences. They're doing dynamic sparsity.
Right. What I like about this method is it is somewhat close to the biology. At least there's, like you said, it's a stone's throw, and we can. It's not that there's a path here to go to potentially really low resolution synapses and low resolution outputs and things like that.
Oh, I
really
see.
covered here, which is kind of nice.
I see that. That's the first time we sort of introduced that sort of low resolution synapses. Is that okay?
I think there's a way to go from this formalism. At least you mentioned this in the past that to go towards really low quantized, low resolution stuff, and you've gone to even binary activations.
Yeah, binary weights, binary activations.
I guess I'm asking. That's our old brain modeling stuff we've done, and in this case, neural networks aren't there, and we want to get there. Do we have alternative? I mean, Marcus just laid out maybe approach. He said, "Hey, it seems to be working."
There are a few other alternates, and Lucas has talked about them before, about other ways of doing dynamic sparsity.
Mm-hmm.
So I think that's to be decided.
I'm specifically talking about the low resolution
The low resolution,
And that's a big win, right?
that's a big win. I
So
think
the
here's
question is, do we have other ways, we want to go there, Marcus said, hey, this seems to work. Are there other ways we know that we want?
this could give us sort of a principled approach in some sense.
Do we have any other ways of doing it? I mean,
Yeah, I think so. I think in just having really sparse networks, it just makes it easier to do low
You're
resolution
saying
anyway,
maybe we
regardless.
could just do it anyway?
Yeah, we could do it some ad hoc way or some,
Uh-huh.
maybe there's some other
Okay,
approach to
so
it.
it's not like we didn't have an idea, we think it'll work when we go really sparse, it should work. This is the first evidence that under this way it works. Okay.
Yeah.
I guess I'm just trying to, it's sort of a binary decision at some point. Do you want to try to, rely on the stochastic models or not?
There's a question when it comes to this desire to reduce the computational cost of not just the synapse but also the synapse training to like get away from double floating point precision, where it's very nice that these synapses are on off. And of course, one can always make an argument that maybe biological synapse doesn't need like 32 bits, maybe like in 8 or actually can't, right? Given that it's discrete vesicles that are being released. But the problem is still that the training method still relies on what you call theta, right? The permanence, which is a double floating point number that keeps moving around and then sets a binary weight at 0 or 1.
So I thought here it may imply that it had to be a high resolution.
A common trend in training neural networks is the part that does need to have some precision is where you're accumulating. You're accumulating gradients. You're accumulating something. That's where the precision matters. And this is where I'm doing that accumulation.
Right.
So there probably are some needs for
so
this
that
to
would
be
be a
pretty
problem
precise.
if you took
Well, I know that
traditionally,
traditionally, but it wasn't just hearing you talk about here. It's not obvious that high resolution is required for this. Or maybe I'm just not understanding.
There's nothing specific here. There's no reason I require resolution that specifically here. But when you train networks, you need to be able to accumulate gradients pretty well. And
one stochasticity that's implicit in there by the fact that you have a finite number of vesicles being released is you have Poisson statistics. So, it's going to get a signal, but it's going to, it's going to be dictated by a certain variance, that looks like, I think, Poisson statistics.
It's just, you can even just bump up another level. These are tiny little biological things, and they just can't have precision. That's it. It's just, it's quantum effects, so it's just crap going on there. So we can just reject the idea that synapses have higher resolution of anything. And the vesicle argument is one, but it just, I don't know. I want to get back to this issue about this accumulating this high resolution stuff.
And just making sure this is about the computational cost of training.
I understand.
So it's not inference doesn't come.
But that's a big deal.
Yeah.
Right. That is, in fact, maybe the biggest deal. So
continuous learning.
I guess it's just not intuitively. I don't have a sense for why I couldn't do your little. I'm getting the right word for your gradient thing there. Why does it have to be high? Why can't you just approximate? I don't know. It's just not intuitive to me why this has to be a very accurate number. Maybe there's a reason I just don't get it. I don't see it. I'm not saying I think it doesn't. I just don't understand it. Why it has to be like? What would happen if you made it less accurate? What would be the failure?
Or the permanence only had 64 steps or 16.
Because I guess like intuition is gonna be that there's some in order to train well, you need to use a learning rate that is sufficiently low.
You want a very slow incremental learning.
Yeah, and there exists some learning rate that is
that's intuition. I get it.
Yeah.
I think I got it.
And that's partly tied to this batch mechanisms of doing.
And it's very much tied to the lack of dendritic segments, right? That you're essentially every synapse has to move a little bit all the time. We don't want anyone getting too ahead of each other. We go through multiple times. And will very slowly settle on.
Yeah, and that's my intuition, when we get to really, really sparse representations like these active dendrites have.
Well, it's as sparse as important as the active dendrites important. The active dendrites basically say, you know, I can train quickly because I know the synapses I'm training are the ones that are important. All these other guys I'm not training at all because I don't have to worry about them.
Yeah, but you don't have to worry about them because it's sparse. The other ones won't even become active.
Is it because it's sparse or because it's compartmentalized
I think
dendrites?
it's because it's sparse, because if they were dense and you had active dendrites, things would be firing all the time. Everything would be firing all the time.
Well, maybe it's both, but I mean, if I had sparsity of activations.
Yeah, maybe it's both. Maybe you need both.
Yeah.
Could I put a straw man out there? The cant on how we train is to take all these, assuming it's a classifier, we take all these things and then we mix them all up so that there's no concentration in one area, and then we kind of feed them through. That's not how we learn. We learn, you know, if we're fixating on something, we're running multiple things through in small variations, and then we cut off and do something else. So that might reinforce the compartmentalization that you're talking about, that only a certain section of the network is actually accurate.
Now we're adding additional part of the theory there, Kevin. Now we're talking about putting in the whole reference frame component of it, because then you can attend to some part of the learning of something is a set of data in a reference frame.
Right.
And when you attend, you're attending to one part of the reference frame, and therefore all the other parts of the reference frame are. So there's multiple levels at which this gets compartmentalized. One is just like dendritic segments with sparsity. The next would be like reference frames.
Right.
But we know that these networks aren't doing any of that right now. So
right. I'm just saying, looking for the negating mechanisms that allow you to only activate certain sections of this network in concert with place or location.
Well, but the problem is we need to get to the point right now. We want to get to the point where we're taking existing neural networks that don't have that stuff at all, and we're not going to introduce reference frames anytime in the near future. Not right away. How do we get to this low precision? Our challenge right now is to get to low precision using existing artificial neural networks or existing applications or existing paradigm of them. It's really clear, of course, as we go to an attention mechanism with reference frames, the displacements, and all this kind of stuff, you can solve that problem.
Right.
But we don't have that here. So given what we have, how do we get to low resolution? That's our goal in the next year or something, to get the low resolution on these things.
Well, one of the things, just to take my straw man a little bit further, is that if you do these episodic trainings on particular tasks, on small variations, your learning rate could be relatively high during that, and then you kind of shut it on down. I'm looking for some way to self-identify these categories and locking things down, not everywhere, but just in those areas where, we have confidence that we found something that has some commonality. So we'll learn.
Again, I'm saying we know the brain is doing this in this much more sophisticated way.
Yes, exactly.
So the question is, do we want to introduce something that's not quite brain-like, but so something similar in these networks?
Yes, that's
and I don't know. I'm not sure if that's worth it. There's I don't know.
I mean, I agree that once we have the rest of the environment in the sense of how the brain localizes these problems involved, it'll get better and better and more human-like in its approach. But I think the first thing is to say, what's wrong with the existing training mechanisms right now that everyone has gone to try to do this, and say, let's break some of those rules and see if there's, we have a model to say, this is, if you break it just the right way, maybe it'll be better.
Yeah, and you're right, although we could go down a huge, long rat hole trying to change the way people think about training, which ultimately we're going to abandon. So that's my concern about something like that. Obviously, it'd be better to get to lower precision without having to do that kind of stuff you're talking about, right? It would be better if we could just get there with sparsity.
Here's a question I've been pondering now. in my understanding, right, one of the reasons why we need so much precision in the error accumulator in like backprop, right, is in part because the contributions are very small and you do these whole big batches and you have all these connections, meaning the error gets propagated to all these little connections. Whereas in a very, very sparse network, most of the time there's going to be no signal at all, and then when there is some error to correct, it's going to be a lot bigger as a proportion kind of the back propagated error. And so in that sense, I am wondering whether that increase in variance in the error signal affords automatically lower resolution on behalf of the accumulator. So what I'm wondering is, can you show?
Subutai just was saying a moment ago, the sparsity gets you there?
Right, so the question is, does sparsity mean automatically, even in the standard existing paradigm, that the error signal acquires so much variance that a lower resolution accumulator will do? So if you test the slope of failure in decreasing the theta resolution, let's say from double to single to some 8-bit thing, does the slope of that decrease in performance change at a different level of sparsity, and how does that change? Because the first order assumption, I guess, at least that I would have now, is indeed that slope would flatten out for a sparser network because you can afford to be less fine-grained in your accumulation.
Yeah, there's a really simple way to think about it, I think, which is, suppose you're extremely sparse and you're 99.9% sparse, right? You're only updating things 1 out of 1,000 times. There's really not much to accumulate. So you don't need a high precision accumulator.
Right.
As simple as that.
Right.
Yeah, but we don't know how to get that sparse, right? So I think what we're saying here is, from where we are today, we're over here, and we want to get them someplace over here. And the first thing we can do is we can say, well, and what we're trying to do is get from these high precision to very, very low precision. And one of the first things we can say, we think if we added sparsity, that's going to help, right? The next thing we say, because that sort of separates out things that need to learn. Then we say, we have active dendrites, or I should say segmented dendrites, really. That's another way of breaking things out, like only trained on some of these, right? And then we know that there's another one we need to do eventually, which is going to be reference frames, and learning objects as a complete thing. And that also helps. That means I only have to train on some part of the object's representation at any point in time. So I guess to me, what we just said, these are 3 steps along the way. Kevin suggested another one, which is, I would call it sort of a side one, like go over here and try different tricks for training, something like that. If you don't mind me calling it that. But I don't think that's kind of on this pathway here. So I guess the only question is how much can you reduce by doing this, and how much does you get from doing that? Is this a fair?
Yeah, and I would put one more in between, which is this temporal memory style predictive, and that could be in between the active dendrite and the.
What would that be? How does that fit in there?
That fits in because with a predictive mechanism, you're getting the error signal very often and very locally, and so you don't need to accumulate much.
But what I promise I see is how does that fit into these kind of networks where we're basically spatial pattern recognizers. The total temporal memory thing, I don't know how that plays into.
That would be a streaming system.
Yeah. So I would agree if we're doing streaming type of analytics or something like that, but we're not really doing that much. I mean, that's sort of, you could say, the way we've always talked about it here, there's, the way I'm writing about it, there's sort of 2 versions of this here. You have, a predictive model. This is a predictive model. This is a predictive model. This is the temporal predictive model. This is the sensory motor.
Yeah, even the reference frame, you would need some sequences. Right?
Yeah. It's these are both types of sequences. The sensory motor sequence is a pure temporal sequence, and so I'm not sure I would question whether that's in between these 2. That's the way we thought about it in our research here, but in the end, if we're going to solve like visual pattern recognition problems, we're going to be doing it this way. If we're going to do temporal things, we're going to do it this way, and the brain does both, of course. All right, so, so maybe we could say that when you have both of these, in some sense, are predictive models, and that helps you reduce your training. So that's another. It's another point. Maybe it's here, maybe it's down here in parallel. I don't know.
I think the predictive models are important in the sense that you're trying. It's like the network. How do you ask the network, what it believes, if you pardon the expression? In other words, if I get an image and a totally disparate image, a totally disparate image, a totally disparate image, I try to find a commonality of that. Well, the commonality is like the low level, B1 or below. If I'm looking at, I get this image slightly displaced with this image, slightly changed with this image, slightly changed this image, then there is there's almost a causal argument that says, oh, whatever the signals I'm getting through here, there's a consistency to them that has the ring of truth.
Yeah. Well, temporal adjacency has a training signal, right?
Exactly.
Yeah. So that's the way we used to think about it all the time, and going back, that was the whole gist of HTM theory.
Right.
But now we know that it's more sophisticated than that, and in that temporal adjacency is applied with this reference frame and attentional mechanism, which makes it much more powerful. So we don't learn a dog as a dog by watching it just moving through space like this and temporally adjacent images. We now know that we built this internal structure of a dog by attending different parts of the dog in a reference frame, and so we have this 3D model of a dog in our head, and that's what's rotating. It's not just these images that are adjacent to each other in time. So,
but that's what we learn from anyway. So
but we don't really learn that way. I used to think that we don't. We learn by attending the components of an object and building that structure of the object.
Okay. And moving around.
We
create the sequences.
We move around the object, but the point is we attend to different components of the object, and those different components are assigned to a reference frame, whether I'm moving, the object's moving, or I'm moving, or both. That's the underlying data structure is the reference frame and the data assigned to the reference frame. It's not just temporal adjacency.
Okay. So let me.
It's and you can't. I don't think you can get there without the reference frame.
Okay.
I used to believe you could, but never.
So do you believe that structuring is hardwired, or is it
hardwired in what sense?
Hardwired in the sense that we're born with that, the grid cells and everything else, so that we're just ready to kind of fill that information in, or how much of that is a learned component?
I think the grid cells are hardwired. They're there. The metric reference frame is there. How it's applied to any particular object, the dimensionality of it, how it's mapped onto different structures, I think can be learned. But you don't learn to have grid cells. They're there. They're like that's a hard-coded mechanism.
But they presumably, just like with young cats, when they before their eyes are open, so they, the delineation of dominances, for edges and stuff like that gets crisper under use. You're basically saying that we're kind of wired to do this thing, but we kind of get better with more use. And
I think I don't know what would happen if you to grid cells if you didn't exercise them. But we can just assume that brains are designed to work this way. They have this structure, just like the hippocampus has this structure for learning environments. The neocortex just has this basic structure for learning objects. It's not a learned structure. It's like filling in the data is the learned part. But that's the way everything works. I'm convinced of this. That everything we know, all of our knowledge about the world is in these reference frames. That's it. Everything. So we ultimately want to get there. We have a long way to go before we get that. I forget what year or what decade you have that in your chart. Right. But it's a long way away. So it's good to talk about it, but practically right now we have to get this to work with existing.
Okay, so what would be the next nearest achievable model that would have that aspect
of the grid cell stuff?
Yeah.
Well, I think the first, I would ask a different question. I thought we were going to, what's the next thing we can do to get to low low resolution multiplies. That's the key thing we have to do next.
All right.
We need to get deep learning networks working with low resolution. So how much can we do with sparsity? How much do we have to do dendrites? I have no idea. We don't want to get ahead of ourselves. I don't even know how we jump ahead to putting these reference frames in yet. I don't think.
Well, there is a representation of the reference frame in the label of classified images. It's just not being used.
What do you mean is a reference frame?
So when you're classifying, 1,000 different dogs, and you have like this one bit, right, in the output that says this is a dog.
Yeah.
The problem is that bit, while you propagate error backward from it and whatnot, it doesn't do anything to the network, right? It doesn't change which synapses are, available. It doesn't recruit parts of a network, right? And so in that sense, there's sort of some idea of of a class, right? But it's not being used as a reference frame.
Yeah, well, it's not implemented. It isn't a reference frame, right?
Yeah, it doesn't deserve that name.
But
if you wanted to
one.
expand out what machine learning does right now, you would start with thinking about what that output unit.
Yeah,
do
maybe if I understand what you're saying, in my mind, what it means to be a dog or a cat is you've locked into in the world of grid cells, you sort of lock down your grid cells to be in one part of this very, very large space, and anywhere in that space is a dog, and anywhere in that space is a cat. Any one of the representations of location in grid cells are unique to the object, not shared among objects. So as soon as you lock down one location in this possible infinite space, then you know you're on a cat or a dog. I'm not sure if that's what you're going towards.
Yeah.
I think at some point we have to figure out how to add really a data structure to these networks that like grid cells and place cells. We are far from being able to do that now. I don't think we're even close to being able to do that now.
So I think fundamental, if I go backwards a couple of layers, is fundamental is being able to separate an object from a background. That's something which you're constantly being bombarded with.
I think that's even the wrong way of looking about it, Kevin. I'm sorry. I get up in the middle of the night, every night, to go pee, and there's varying amounts of light in the room, from almost pitch black to this last few nights there's been a lot of moon, and I know exactly where I am, and all I need is the slightest little input to know exactly where I am and what things are and where the cup is on the counter and so on. And it's not like I don't have this problem of separating input from output. I have this model of the world. The model, as soon as I look at myself in the model of the world, then all separation of background is taken care of. I know, because I know where everything is. And all I need is the slightest little input just to re-anchor myself. And so it's not like I look at the world and say, oh, it's all gray. Where is the edge of this kitchen sink? And where is the edge of this? I don't do any of that. Once I know where I am in the world, then I know all those things are. It's not a problem of separating out the background. It's a problem of knowing where you are, knowing your location. And so if you don't have this idea of a reference frame, if you don't have an idea of what the structure of the world is, then you're tasked with separating out, you're tasked with constantly taking your input and figuring out what it is. But in reality, once I have a model of the world, I don't have to take my input to figure out where I am, whatever everything is. All I need is just locate myself.
I don't disagree with that, but
I guess I'm arguing that separation of background from foreground is not really an interesting problem.
I think it's if you don't have that, you don't get to what you're just talking about. That's because that's an evolved, derived model based upon some set of experiences. But if you're starting off, fresh and trying to build up a hierarchy of,
So, but imagine this, if I would take an image and I'm looking at something, I don't understand it, I don't separate the background from it. I attend to some smaller and smaller piece of it until I say, oh, I know what that is. And so I don't deal with this like I don't know where the extent of this new object is. I don't do that. So I just attend down to smaller and smaller spot until I recognize something. Okay, I know what that is. and then, oh, here's another thing, I know what it is, and now I start building up structure by attending one component at a time.
I agree.
Okay, so I guess I'm just trying to get away from this idea that this separation of background and foreground, which I've always been peeved about, so excuse my
No, I understand, and I say once your panoply of models is sophisticated enough, you can do all these shorthands. But I would say that there's, if you look at how you get stepwise to that, you don't spring forth as a baby with this ability. There are levels of learning and adaptation to the environment, whatnot, that eventually get to the point where I don't need all that stuff. I don't need the background separation. I can just pop and do that. But I don't think you do it, by training a network to that necessarily. I think that there is an auxiliary processes that go on that guide you to the point where you can do that.
I don't know. I guess I think it's a red herring. I mean, think about.
I have to make a phone call.
Okay. Think about how we learned something as simple as reading or anything. You take a child, you train a child. You always present them in the clearest, simplest, isolated form as possible.
Right.
Here is one letter, black on white. It's like you don't start off with some florid, font that's in the textbook. It's like, and so we're really not good at separating background from foreground. We just really don't do well at all at that. So instead, we present things that are very, very clear and simple, one letter at a time, then one word at a time. And so I think it's an incremental build-up problem. But we don't. I guess I'm just reacting to your comment that we have the big problem of separation of foreground and background. I don't really think that's it. I think the question is, how do we build models? How do we build this model piecemeal, slowly, one step at a time?
Well,
we don't have to resolve this now. You can agree to disagree about it. I guess the real question we have. I just want to get in focus. Right? It's fun to talk about this stuff. We have to get there, right? About reference frames and so on. Right? Because right now the question is, how do we get these networks to have low resolution? I'm going to leave that as the sort of the topic of the day. And I think we should talk about future, right? How we're going to slowly increment. My problem with introducing reference frames now is we don't understand how they work well. We don't understand how grid cells work. We don't understand how orientation works. We didn't get to the bottom of displacements. So I know that's like a huge can of worms here. We just haven't got look at Marcus because he knows this. We're not even close to understanding it well enough to implement it. So I don't want to focus on that yet. I think we should focus on the stuff we can do today, and try to figure out the rest of that later.
Lucas had a question like half an hour ago.
Sorry, Lucas.
He said, Marcus, did you observe similar results as you're showing here in any different data sets?
That is one thing. This is all one data set. That's my answer.
There's also one architecture, right? It's the
yeah. So I've also done AlexNet, converted it using this method, and I did that to try fully binarized ones where the weights and activations were binary, and that also worked. So yeah. So I did do a different architecture, but not a different data set. I think we might be done.
Yeah.
Before I end the stream, Lucas asked me to get a better picture of this.
Sure. Yeah.
So I'm just going to move the camera around. So we'll be live for just a minute more.
Cool.
Thanks, Marcus. It was great.
Cool.
Yeah, it was a nice shot.
Here it comes.
That was a nice presentation.
Disconnected.
And nice results.
All right, this is much better.
Thanks, Mark. Well, what's the term for that?
Photobomb.
You're photobombing your own
Whiteboard bombing.
You're photobombing yourself. That's interesting.
Right. I'm hoping you guys can pause the video, take a snapshot of that.
I'm trying to see how the piece materials are going here. My wife's watching.
All right, there's another one.
Oh gosh, she stopped watching.
It's frustrating.
Yeah,
And then
I watched the first witness, and after that, I
figure that out
wanted to
yourself.
listen to Nuna's interview or question.
I was watching a little bit of it.
All right, that's much better. All right, pause the screen if you need to write this stuff down. I'm gonna go. Thanks for watching, everybody. Appreciate it. I'm gonna stop the stream.